We're going to play a game that you learned in Sesame Street. One of these things is not like the other. I've got two lists here. And the list on the left has something in common. The list on the right has something in common. And the two lists are different from each other. With your neighbor, try to find the commonalities and try to figure out what it is that's different between the left list and the right list. With your neighbor, go. You are talking with your neighbor. Okay, brave soul, raise your hands and explain.
Stuff on the right is stationary.
Stationary, okay. Stuff on the left is, for the most part, moving. What else?
Both have a rhythm just depending on if you are moving or the object is moving.
Okay, so both of them involve a rhythm. Can I call that a repetition? They repeat over and over again?
Cyclical.
Okay, so if I look at the flashing traffic signal, it stays in one place and flashes in a certain interval of time. If I feel the pulse in your wrist, supposing you have one, it doesn't go anywhere, okay, but it just keeps repeating that pulse over and over again in time. When it stops, call someone. Likewise with everything else. Whereas these things are spread out, okay? Long string of boxcars, pages in a notebook, telephone poles beside a long highway. So these are things that repeat themselves, but not in time, but in space. So what we've got over here are temporal repetitions, repetitions in time at one location. Here, we have repetitions in space at one time. All of these things here we could take a picture of, a snapshot of, freeze them in time, and there would still be the repetition. My point with this exercise is that waves are both. Waves are both a repetition in space and a repetition in time, and we need to combine both of these attributes to understand a wave. Now, a wave results from a periodic disturbance. I do not know, but I have it on good authority that it's been there for a long time, and maybe it's just to see how long it takes us to notice. Not my newspaper. Okay. Now, if I take this wave machine and just create a single pulse, that single pulse travels down and then it bounces back. The bouncing back we'll deal with in tutorial. But that's just a single pulse. If I send a series of pulses at regular intervals, at regular time intervals, what results is a wave. Okay? Now that wave has many characteristics that we're familiar with. It has the same period as the disturbance that creates it. Folks, I can't say that loud enough or slow enough. You cannot have a wave with a different frequency than the disturbance that is creating it. Okay? You think of this wave as a series of pulses. Well, the same frequency at which you're creating the pulses is going to be the same frequency of the wave itself. Now we can talk about the amplitude of each pulse, how far the medium that's carrying the wave gets away from equilibrium. We can talk about the timing, the period or the frequency, and this is just the same as in simple harmonic motion. This is the new piece, the wavelength. If I look at this wave that I've created, the distance from crest to crest, we call the wavelength. Now, if I just send a single pulse down there, well, I can't define a distance from crest to crest because there's only one crest. So a pulse does not have a wavelength, a wave does. And finally, the speed. Folks, it shouldn't surprise you that the speed of a transverse wave is given by this formula right here. And the speed of a longitudinal sound wave is given by this value right here. If a wave is just a series of pulses, well, the wave's going to travel at the same speed that the pulses are traveling. The pulses make up the wave. So this result we derived last time is still good. Now, a repetition in space and time. What I'm going to do is I'm going to set up a wave. I want you to get out your cell phone and use it as a camera to take a picture. Take a picture right now. Okay, too late. I took the picture for you. Okay? By taking the picture, we freeze time. Time is 12 noon. Okay? Boom. 12 noon. For the whole picture, 12 noon. Okay? Now the amplitude is the furthest that any part of the medium gets away from equilibrium, either below in a trough or above in a crest. The wavelength is the distance from crest to crest, or from trough to trough, or you could go from equilibrium to equilibrium if you're careful. You have to go from equilibrium going up to equilibrium going up. If you just go from equilibrium going up to equilibrium going down, you only get half of a wavelength. So it's simpler, and you make fewer mistakes if you go from crest to crest or trough to trough. Okay? Now, I like to think of these wavelengths as boxcars on a train. With a lot of trains, the boxcars are all about the same size, and we call that wavelength lambda. Okay? Now, because that lambda is a wavelength, its units are, well, its length. So it would be meters. And counting boxcars is like counting waves. We're going to use that in just a minute to solve one of our problems. Now, suppose instead of freezing time, I freeze position. And I do that by painting this rod right here with a very bright phosphorus paint. And then I put a black light here, and I turn off the lights in the room, but I turn on the black light. So that your eye is drawn to just this one rod right here. You ignore the rest of the machine. And as the wave goes by, what you see is that one rod is going up and down, up and down, up and down, up and down, in simple harmonic motion. Okay? Now if I plot that position or displacement away from equilibrium as a function of time, it would go up first and then down and then up, and then I get lazy and I just don't take very many points. Now if I had been more careful and taken more points, I would have gotten something that was sinusoidal. Okay? Now again, the furthest we get away from equilibrium we call the amplitude. In this case, from crest to crest or from trough to trough is measured in seconds. So it's the period, the time it takes for that one rod that we were concentrating on to make one complete oscillation. Okay? Now, where in this graph would I find the wavelength? Brave soul, raise your hand. Yes.
Equivalent to the period.
Is it? Because one's measured in seconds and the other's measured in meters.
Not in this case.
The frequency is related to the wavelength.
You add together the amplitude?
Okay. We're going to find a relationship between frequency and wavelength. But just looking at this picture, I cannot, just from this picture, figure out what the wavelength is. It was a trick question. We froze position when we made this graph. We said, only concentrate on that rod there, ignore all the other rods. And as soon as we ignore the other rods, we lose all the information about that wavelength. My point is that we need both of these graphs. That when we freeze time, we get the amplitude and the wavelength. If we freeze position by following a single piece of the medium, we get the amplitude and the period. We need both in order to describe the wave. This would be the spatial repetition, and this would be the temporal or timing repetition.